Thank you everyone for joining us. So our first speaker today, Mile Gao from the University of Queensland, who will speak about understanding the interplay between charge transport, luminance efficiency and morphology in OLEDs using a combined computational and experimental approach. So when you're ready, please go ahead.
Okay, thanks for the introduction, Bronson. I'm Mile Gao from the University of Queensland, and I'm currently doing my PhD under the supervision of Professor Paul Byrne and Dr. Mantas Pivrikers. As mentioned, I will be talking about understanding the interplay between charge transport, luminescence efficiency, and morphology in OLEDs using a combined computational and experimental approach. Okay, first, this is a typical device structure of an OLED. It has different layers, each performs its own functions. The most important one, the emissive layer, it is comprised of guest and host. And normally, emissive guest material is blended with a host material at relatively low concentrations, from 3 to 15 weight percent, to reduce the concentration quenching. It has been well studied that with a concentration increase of guest material, the photoluminescence quantum yield, or the POQI, will decrease. But there's another effect of the gas concentration, which is the effect on the charge transport in the emissive layer. For example, the common used host material, TCTA, it has an ionization potential of 5.8. Another common used emissive material, RP, its IP is 5.3. So when RP is blended into TCTA, it would be expected to act as a trap for hole transport. It can be predicted that these traps will more or less hinder the hole transport. And compared with the concentration effect on POQI, field reports reveal the effect on charge transport. And we know that charge transport is directly related to the charge balance and recombination zone. So this is the focus of the work, to have a picture of hole mobility in the balance with different doping ratios. Before we start to measure the mobility, there are a few techniques that we consider: the time of flight, the space charge limited current, the OFAT mobilities, but they all have their own drawbacks. And finally, what we choose is a mid-sleeve, which can be used to selectively measure either hole or electron mobilities in the films with thicknesses close to those used in operational devices. This is a schematic of device setup for mid-sleeve in the case of electromobility measurements. There are some animations in this slide, and they might not be played correctly because we are zooming in, so I'll just explain them.
Excuse me, Mile.
Yeah.
Do you mind maybe me to move a little closer to your microphone? You're cutting out just a little bit. Speak a little louder, perhaps.
Sure. So here's a schematic of device setup for mid-sleeve in the case of electromobility measurement. First, we apply a high reverse bias on the aluminum side. It should be high enough to inject some of the electrons through the organic layer to the organic and insulator interface. And then we apply an increasing triangle pulse. Those accumulated charges will then be extracted. Is it still fluctuating, my voice?
I think it's working fine now. Yeah, that's better now. Thank you.
Okay, thank you. So Oh yeah, so we apply an increasing triangle pulse and it will extract those accumulated charges. And now this transient can be recorded from an oscilloscope, and by analyzing this, the position of the extraction peak, we can know what the mobility is. Oh, sorry. And using this method, we measured the whole mobility of films with different gas concentrations. We can see that with just the 1 weight % doping of RP, the mobility decreased more than 1 order of magnitude. This decrease in mobility is consistent with the introduction of RP-based traps for holes in the TCTA. And then it continued to decrease along with more RPs are doped in. At around 10%, it reaches its minimum, and then in turn, it starts to increase with the increasing of RP concentration. And finally, at 50%, we can see that it's pretty close to the neat RP film. This would suggest that once the RP concentration is above a threshold, a whole transport pathway might be formed, which enables the host to migrate across the film through the RP component of the blend film. But we also need to consider the photophysical properties apart from the mobility. So we also check the concentration effect on photophysical properties. We measure the PLQY, the PL spectra, the PL lifetime, and calculate the excitance quenched versus the gas concentration. First, PLQY. We can see that for the films containing 1 to 10 weight %, the PLQY, they are pretty high at 80 to 85%. But when the doping ratio increased to 20%, it decreased significantly, and to 50 to the neat RP, it decreased a lot along with the concentration. We can also see from the fraction of excitance quenched, the 1 to 10 weight %, there's no luminance quenching within the range of error. But from 20%, the ratios of excitance quenched increase a lot. It reached about more than 20%. And for 50% stopping ratio, more than 40% of excitance are quenched due to intermolecular interactions. And for PL spectra, even 20 weight %, the green one, has some emission from TCTA. But within the sensitivity of this experiment, the 50 weight % blend has only RP emission. For PL lifetime, we can see that from 1 weight % to 20 weight %, the lifetimes, they are pretty close, all in the 1 microsecond time scale, which corresponds to the first fluorescence lifetime. But for 50 weight %, the lifetime decreased to 0.78 microsecond. From all these photophysical data, it seems that the variation of photophysical properties with concentration, it follows a different regime as charge transport, because charge transport, it decrease to minimum and then increase. So one of the potential answers to why they follow different regimes is the morphology. Because the gas distribution in the emissive layer, it will greatly affect how it performs. For example, whether they are distributed evenly or they are accumulate near the electron transport layer or in the bottom, or they aggregate. But it's difficult to identify the specific position of RP in host just from experiments. So we model the evaporation process. Here are the parameters we used in the modeling. The molecules were randomly deposited onto a graphene sheet. Finally, we deposited 14,000 molecules and formed film about 11 to 14 nanometer thick. And here is a final film morphology for different RP concentrations with the TCTA removed to highlight the distribution of the RPs. As expected, the RP molecules are distributed throughout the film in all cases, but they show the tendency to aggregate in the simulated films. And the prevalence of two RP molecules lying in close proximity in the film is significantly greater than expected for full randomly distributed molecules. But that's just from our eyes. Next slide, we quantify the level of aggregation and its impact on charge transport. Before the quantification, there's one term, the cutoff distance, that we need to consider. The RP complexes were considered coupled if the distance between them, between the iridium atoms, was less than 1.4 nanometers. Based on this cutoff distance, the size of RP clusters can be quantified in this figure. It can be seen that even for the 1 weight percent blend, 15 of the RP complexes are part of an interconnected cluster of at least 2 molecules. And in the 6 weight percent, less than 50% of the RP molecules can be viewed as being isolated. And for an RP concentration of 10 weight percent, the majority, about 70%, RP molecules are part of an interconnected clusters containing 3 or more molecules. And for 20% blend film, only fewer than 5% of the RP molecules are not part of a larger cluster. For 50%, we can see that almost all the RP molecules belong to a huge interconnected RP cluster, which form a single large cluster. So this can kind of explain why the 50% film has a pretty similar mobility as a neat RP film, because they all transport through RP film. And as discussed earlier, the relative energy levels of RP and TCTA means that RP can act as a trap for holes. So here, still based on that cutoff distance and the quantity of isolated RP molecules, we plot this trap density versus gas concentration figure. It can be seen that for 1 weight percent, increasing from 1 weight percent, increase the number of RP molecules led to an increase in the number of traps up to a concentration of 10 weight percent. And then the trap density decreases with the increasing concentration. And in the 50 weight percent, nearly all RP molecules are interconnected. As a consequence, there are few effective traps. And most importantly, this figure is almost the mirror image of the mobility gas concentration figure, the black line in this figure. So this makes sense because more traps, here the traps reach the maximum, so here the mobility reaches minimum. This further validates the use of both experiments and simulation. But these are just the size of clusters. What will make it more efficient is how far the network or the cluster can connect. Here, the final aspect considered was the span of the networks of interconnected RP molecules in the direction perpendicular to the substrate. because it will be most efficient if the network can connect the layers under it and on it, so that it will form a perfect charge transport tunnel. The left figure shows a visual representation of the networks of RP that are connected from the bottom. We can see that in one-way just a few, very few, connect from the bottom. 6-way percent, 10-way percent, they just have few networks and they can't span further. From this figure, we also plot the number of networks versus the network's vertical span. From 1% to 10%, that's the black, blue, and green one. They don't have the networks that can span through the film. But from 28%, the yellow one, and 50%, they can span the whole film. At 20%, the large networks are observed that span the entire layer from substrate to surface. And 50%, almost all the molecules belongs to such a single interconnected network. That is, almost all of them are connected from the bottom to the surface. So the whole transport would be expected to occur primarily through the networks of RP molecules in the films containing 20% and 50% of RP. And this can explain the measurements of mobility, why 50% has a close value with the neat RP, because all the holes are moving primarily through the RP phase, with the TCTA playing a minor role. Okay, finally, it's possible to propose the unified model. We showed that incorporating just the 1-weight% of RP into the blend led to an order of magnitude decrease in hole mobility. This is consistent with traps for holes being introduced into the film. And the further increase of concentration to 6 and 10-weight%, it does decrease the mobility, but not as large as might be expected if all the newly introduced RP molecules acted as individual traps. This, based on the simulation, it suggests that although there are a greater number of RP molecules, these molecules form clusters and networks through which the holes can migrate through portions of the film. And in 20-weight% and 50-weight%, the simulations predict that there's a very high probability of networks that span the whole film, so the mobility increase. And for 50% and neat RP, they're pretty close because 50% has big networks that connect from the bottom to the surface. And now let's turn to the photophysical properties. Remember that we say they follow in different regimes. The POQIs, for example, from 1 to 10-weight%, the POQIs are high and they follow and they are all in the 80 to 85% range. But when the POQI increases to 20%, when the concentration increases to 20%, it decreases. So it follows a different regime, hence we vary the cutoff distance in this figure. And we found that the 0.9, the blue line here, the 0.9 nanometer cutoff distance corresponds best with the POQI data. With a less cutoff distance, the 1, 6, and 10-weight% films, they have the very small amounts of connected RP. So here is a fraction of isolated guests. So in these three conditions, most of them are isolated. So there are less intermolecular interaction, there are less quenching. But with the concentration increase to 20%, the fraction of gas isolated decrease a lot. This point corresponds to the 20% here, which led to a decrease in the PLQI. Okay, so finally, in conclusion, the photophysical and charge transport properties of the film have significantly different gas-gas distance dependence. For the hole transport, the hole hopping happens when the edge-edge distance between RP is less than 0.4 nanometers. But for the PL quenching, it happens when RP molecules, they are intercalated because normally the radius of RP molecule is about 1 nanometer, and we choose a 0.9 nanometer cut-off distance, so they should be partially intercalated. And the hole mobility is measured using mixed sleeve, and the photophysical properties corresponded closely with those inferred from the film morphologies obtained by simulation. So they validate with each other. I would like to thank my supervisors, Professor Polburn, Dr. Amantas, and also thank Professor Allen, Dr. Tom for the simulation, and Dr. Paul Shaw. And thank you for your attention. That's it.
Thank you very much, Mile. Very interesting talk. We have a couple of minutes for questions. If anyone would like to ask a question, please remember you have to unmute yourself in order to speak here. If anyone has any questions. If not, I'll ask you a question. So I see that you've measured the hole mobilities. Obviously, also the electron mobilities would be interesting. Can you give some comment? Would you expect a similar trend for electron mobilities?
For the electromobilities, yeah, we do consider the electromobilities, but here we just, because the energy difference, it can be viewed as hole traps. And also because the energy difference, the doping of RP, it can also act as electron traps. So we didn't measure it, but from this system, from these predictions, we might expect to see the electron mobility that will be high in the beginning, and then with the doping of TCTA, it will decrease because TCTA is not is a hole transporting material and electron blocking material. Basically, that's what we expect to see.
All right. Yeah, you're cutting out a little bit at the end there, but I think I got it. So thank you. Does anyone have any other questions for our speaker? Okay. If we have no questions, then everyone please join me in thanking Mile. We can't really do a round of applause very well over Zoom, but thank you very much. I'm sure everyone would agree that was an interesting talk.